In an earlier recording, we discussed linear dependence or independence of n vectors in n dimensions. The number of vectors was the same as the number of dimensions. Here I want to look at what happens when these numbers are different. I'm going to use an example of 3 vectors in 4 dimensions. 4 dimensions, I hear you say. I can't picture that. Well, it's true, we can't picture 4 dimensions, and we also don't use I, j's and k's. Instead, we simply write the vectors as having 4 components. Mathematicians are quite happy with such a concept. Such vectors can be manipulated in the usual ways, even though we can't picture them. Here are my 3 vectors. So my question is, are these vectors linearly dependent or independent? Now, in fact, I've just made up the numbers at random, and when you do that, there's quite a high probability that they will turn out to be linearly independent. However, we need to work that out mathematically. We have to remember what it meant for vectors to be dependent or independent. The definition of linearly dependent is that we can combine the vectors using multiples, constants. I'll call them C1, C2 and C3, in such a way that, when combined, we get the 0 vector. Something like this. UV and W are dependent if we can find C1, C2 and C3 not all 0, such that the combination C1U plus C2V plus C3W equals 0. Now you'll recall in the earlier recording what we did at this stage was to write the U, V and W as columns, and then rewrite the equation as a column vector equation. Let's do that on the next page. It would look like this. We then turned those columns into a matrix and wrote a matrix equation. Something like this. The matrix A just consists of the columns of the vectors U, V and W put together into a matrix. Notice that now A is 4 by 3. It has 4 rows and 3 columns. It's no longer square. When we looked at this situation before, we had n vectors in n dimensions, and so we were dealing with a square matrix. There we had the luxury of having the determinant at our disposal. We could evaluate the determinant and decide whether it was 0 or non-zero. That told us something about the linear dependence or independence. In this new situation, a 4 by 3 matrix does not have a determinant, so we don't have that method at our disposal. Instead, we've simply got to bite the bullet and do the Gaussian elimination. We'll start to set that up now. I'll write out my A again, and then do some row operations. Initially, I'll try to get a column of zeros underneath the first 1, so a first column of 1 with zeros below it. I've already got 1 0 in place in the bottom left corner. I need to manipulate rows 2 and 3. I'll write down the rules and then just do the arithmetic. You can halt the recording and check it if you wish. To get rid of the 2 in the second row, we need to subtract 2 of row 1. To get rid of the negative 1 in the third row, we need to add 1 of row 1. Here's the result. At this point there are various paths down which we could tread. What I'd next like to do is to get a 1 in the position 2, 2. I'll circle that. I'd like a 1 in this red circled position. I'm looking at the bottom row and seeing that 3 is a factor. So I could divide through the bottom row by 3 and then swap it up to the second row. That'll put a 1 exactly where I want it. Let's do that next. Okay, so I'm dividing row 4 by 3 and then swapping it with row 2. That means that the first row and the third row will stay unchanged. Let's fill in the rest of the numbers now. Let's put a 1 where I want it. I've circled it. I'm now going to do further row operations and use that 1 to get rid of the 6 and the negative 3 below it. That means we need row 3 becomes row 3 minus 6 row 2, and row 4 becomes row 4 plus 3 row 2. That's the next stage. I'll write it out. There, take a moment to check it if you like. We could carry on doing further Gaussian elimination processes, but actually we've got enough information here to solve the problem immediately. Both the third and the fourth rows are simply telling us that either -8 times C3 or alternatively 4C3 must be 0. In both cases that means C3 is 0. Okay, fair enough. Now what about the second row? The second row tells us C2 plus 2C3 equals 0. But we already found that C3 was 0, so that means that C2 must be 0 as well. Finally, row 1. It tells us that C1 plus 2C2 plus 3C3 equals 0. Since both C2 and C3 are already 0, that means that C1 is 0 as well. The Gaussian elimination has told us that all of the C's have to be 0 for the equation to work. That means that these vectors are linearly independent. There is no non-trivial combination of them that comes to 0. All the coefficients are 0. That's the only way it can work. That's concluded the exercise, and it's all I want to say on this topic here.